In this video, we're going to study a very powerful tool that will allow us to determine whether a series is absolutely convergent or divergent. And you will see that it's going to be extremely helpful when we talk about power series later on. So the ratio test tells me that if I know that I have a series whose terms are never zero, and I suppose that the limit of an plus 1 over an is equal to L, and this includes the possibility of L equals infinity, just to make the discussion a bit simpler. If I know that L is less than 1, then the series is absolutely convergent. If the limit L is greater than 1, including L equals infinity, then my series is divergent, but, huge warning, if L is equal to 1, the ratio test is inconclusive. I cannot say anything about my series, other than I don't know anything about it. So, of course, this is very nice and very powerful when the limit is less than 1 or greater than 1. When you try to apply the ratio test and you find that the limit is equal to 1, you just have to do something else, because this is absolutely useless. But that's okay. So let's take a look at how to use the ratio test in an example, and after that I'm going to give you the proof of the theorem. So, we want to find whether the series is conditionally convergent, absolutely convergent, or divergent. And we have these. The series n equals 1 to infinity of negative 1 to the n times n over 3 to the n. And we want to use the ratio test with an equals to negative 1 to the n times n over 3 to the n. So we just have to create this quotient of an plus 1 over an, it's this big bulky thing. And now we just need to massage this expression. I just want to put it into just one fraction. So we do some computations here. Well, negative 1 to the n in absolute value is always 1, so I can just ignore it. And now when I put it all into one fraction, it looks like this. So we have 3 to the n times n plus 1 over 3 to the n plus 1 times n. And here I can see some simplification. So you have 3 to the n in the numerator and 3 to the n plus 1 in the denominator. So we get 1/3 times n plus 1 over n. But n plus 1 over n converges to 1 as n goes to infinity. So this limit is just 1 over 3. And 1 over 3 is less than 1. So by the ratio test, I know that my series converges absolutely. Let's now take a look at the proof of the ratio test. But before we jump into the proof, let's just very quickly take a look again at the statement of the theorem. It tells me that if I have a series of terms that are not zero, and I look at the limit of the ratios of the an plus 1 over an, if the limit is less than 1, then my series is absolutely convergent. If my limit is bigger than 1, then my series is divergent. And when we say L bigger than 1, we're also allowing the possibility of L being infinity. And when L equals 1, we cannot say anything at all, other than we have no clue what's going on with that series. So, where we're going to prove it is we have to look at the cases when L is less than 1, when L is bigger than 1, and then we're going to see that when L equals 1, we could have both cases, that the series could be divergent or convergent, so we cannot draw any conclusion. Okay, so we're going to assume that the quotient an plus 1 over an in absolute value converges to L, where L is strictly less than 1. And now, my idea here is that I'm going to compare this series to a convergent geometric series. I know, sounds insane, but you will see in a minute how we can do it. So since L is strictly less than 1, I can choose a number r that is in between L and 1. Okay, so we have this r between L and 1, and this is what I'm going to do. I know that the limit is L, and I'm going to take epsilon equals r minus L. This is a positive number, so it's a valid epsilon. And because of that, I know that I can find a natural number n naught, such that for any n greater than or equal to n naught, the absolute value of an plus 1 over n is less than L plus epsilon. Here I am using the definition of limit. But L plus epsilon is the same as L plus r minus L. So this is just r. Okay, So now if I look at this, then I can use this, and I know that for any n greater than or equal to n naught, an plus 1 is less than, well, the absolute value of an plus 1 is less than the absolute value of an times r. And now I'm going to use this. So for n equals n naught, I have that the absolute value of an naught plus 1 is less than the absolute value of an naught times r. But now I'm going to look at, well, what is the absolute value of an naught plus 2? Well, this is less than the absolute value of an naught plus 1 times r. But an naught plus 1 was less than an naught, well, an absolute value times r. So we end up with the absolute value of an naught plus 2 is less than the absolute value of an naught times r squared. And I will continue doing this process. And, well, you can prove by induction that in general, the absolute value of an naught plus k is less than the absolute value of an naught times r to the k for any k greater than or equal to 1. And here we got this r to the k. We know that r is less than 1 because of the way we picked it. So that is the one that is hinting at me, geometric series. Indeed. So you see, this series here of the terms that we have, remember, an naught is just a fixed number. So the absolute value of an naught is just a constant. It doesn't affect the convergence of my series. Then we have the sum of r to the k where r is less than 1. So this is convergent because it's a geometric series with r less than 1. And then, well, we got that inequality of the absolute value of an naught plus k is less than an naught times r to the k. So then the sum from n equals n naught plus 1 to infinity, which is the same as saying the sum from k equals 1 to infinity of n naught plus k. This converges by the comparison test. Oh, okay, that's very good. Then my series, the absolute value of an is convergent, because remember that a finite number of terms doesn't affect convergence. So here we're summing starting from n naught plus 1 versus summing starting from 1. But as I said, I'm just throwing away n naught terms. I'm throwing away a finite number of terms. So that doesn't affect convergence at all. And that's how we know that then my series of an is absolutely convergent. Great. Now, what happens when the limit of the ratio of an plus 1 over an converges to some number L that is strictly bigger than 1? So there could be the number L, real number L strictly bigger than 1, or that it diverges to positive infinity. Well, in both cases, I can find an n naught such that this ratio of the absolute value of an plus 1 over an is bigger than 1 for all the terms that are greater than or equal to n naught. Try to think about why this is the case. I'm sure you can write down a proof of this. For both cases, remember, you have to separate it into two cases and use the definition of limit, but I'm confident you can do this. Okay, so we have this. But that tells me, in a way, what I can see from here is that the sequence of the absolute values of the an's is increasing starting from certain points. So it eventually is increasing. Okay, so after n naught, my sequence, all the terms of my sequence are increasing. I know that the absolute value of an naught cannot be 0, so it's positive, and this is because, remember, none of the terms of my series are 0. So we have an increasing sequence, and the first term that we're looking at is not 0, so the limit has to be, if the limit exists, it has to be bigger than 0. So we know that the limit is not 0, and if the limit is not 0, what happens? If I know that the limit of the an's is not 0, we know that my series has to be divergent. Okay, very good. So we know that if L is less than 1, my series is absolutely convergent. If L is greater than 1 or the limit is infinity, then we're divergent. So what happens with L equals 1? Well, I will ask you, can you think of a convergent series such that the limit as n approaches infinity of an plus 1 over an is equal to 1? Can you think of a divergent series such that the limit as n approaches infinity of an plus 1 over an is equal to 1? I invite you to pause the video and try to find examples of these two cases. One example of a convergent series such that the limit of this ratio is 1, and a divergent series such that the limit of the ratio is equal to 1. And just think of the typical examples that we always use, that the ones that we've used over and over again, and I'm confident you will be able to find it. So please pause the video, and when you have the two examples, come back. Welcome back. I hope that you have your two examples ready. The first one, well, we know that the series of 1 over n squared converges. We've talked about it over and over again. And when you look at the ratio, well, you end up with the limit of n squared over n plus 1 squared, and that converges to 1. And now the harmonic series, we know it diverges, and when you take the ratio, you end up with n over n plus 1, and that again goes to 1. So here we have an example of a series that is convergent, that the limit of the ratios of the an plus 1 over an goes to 1, one that is divergent, so that's why we cannot conclude anything. Anything could happen. So again, whenever you apply the ratio test, if you find that the limit is equal to 1, the only thing that you know is that you need to do a bit more work to be able to find the answer to the question, is this series convergent?